Good afternoon, everyone. Thank you so much for inviting me here, and thanks, John and Ashley, for organizing this. So I'm Ryan McGorty. I'm at the Physics and Biophysics department at University of San Diego. I think Ray and Pete already talked a little bit. Maybe they didn't use this image, so this is another view. And I'll talk about the work that's done in my lab, right? So I really just want to focus on these students. These are the undergraduate students in my lab. It looks like a lot, but actually they repeat themselves. We only graduate about 10 physics students a year, but we have both physics and biophysics majors. So I'll talk about the work that they do. And so last week I just went into the lab, was like, hey, what are you guys doing? Here's Rulin. He's building this new microscope, DIY, for looking at, we're actually developing a new method for detecting nanoparticles diffusing. And he's a junior physics major. Michelle, she's a senior physics major. She's getting plenty of grad school acceptances in the last couple of weeks. She's been working on our custom-built light sheet microscope to look at shear and how that affects fluid-fluid phase separation. I'll talk a little bit about that project. And I also have John Brady. He's a biophysics major. And he's using this instrument, which we just got installed, thanks in a large part to the support of the Research Corporation. So he's looking at simultaneously measuring the rheological properties of fluids and looking at the microstructure. And I'll talk more about that. So all those projects involve the use of colloidal particles, and I'll speak a little bit about what colloidal particles are. Maybe you already know, but they're basically particles on the order of a micron, much larger than a molecule, but still small enough to diffuse around and self-assemble. And these can be made of various things. We generally make them out of polymers. And we control the particle-particle interactions pretty well through various means. All right, so why do we study these just spherical plastic beads? They're pretty featureless. Well, there's a couple reasons. One thing we do is we look at phase transitions, phase separation with these particles. If we introduce a solution of these micron-sized or a few hundred nanometer-sized particles, add some polymer, we can get these particles to group together. They can phase separate, and we can actually observe this phase separation on the particle scale. So this is just a video here showing that we've kind of introduced that attraction. And so these particles aggregate together into these liquid droplets, right? And so if you can't see it in that video, I'll just show in the still image. What's nice about studying phase transitions with these micron-sized particles is that we can optically track and observe each individual particle, right? And we do this not just with fluid-fluid phase separations, but also crystal or solid phase transitions. So here's just a cuvette of our colloid polymer system. We can get triple phase coexistence. We can study crystal structures, and again, observe those on the individual particle scale. That's a nice thing about using colloidal particles. We also have some projects underway currently looking at the gel transition. So starting from a fluid state, if we tune the temperature, we can get it to gel and then look at that, enter back into a fluid state. All right, so this is one kind of area of research in my lab looking at phase transitions with these colloidal particles. Another area, or another reason that we're looking at colloidal particles is to study how these dispersions respond to shear. And this is a project that just has been started this year. So funding from the Research Corporation through a Cottrell Scholars Award was able to kind of generate some early results and allowed us to convince the NSF to fund a rheometer. And that rheometer just was installed last month. And this is actually a collaborative proposal that brought in this rheometer between myself and Ray Anderson and Pete Iavini and a couple other faculty at USD. So a lot of Cottrell scholars were on that. All right, so what we want to do with this is, you sandwich your sample between two plates. In our case, with our rheometer, the bottom plate is made out of glass, so we can put an objective lens underneath and observe the microstructure, observe this colloidal dispersion as we shear it, right? Because what we want to do is link together the rheological properties that we measure with the rheometer with the structural properties that we observe. And it's kind of well known that the non-Newtonian behavior you can get out of colloidal dispersions has to do with how whatever's dispersed in the fluid, how that's structuring. And maybe if the particles kind of line up in the direction of flow, you might get shear thinning. If they aggregate together into clusters, you might get shear thickening. So we've started doing that with our colloid polymer samples, where when quiescent, we just have these spherical droplets of colloidal particles. When we introduce some shear, you can see they start to stretch out, kind of in the direction of shear, which is in the vertical direction here. If we really crank up the shear, we'll get these kind of lane formations, right? Where, again, the direction of shear is vertical. All right. So now I also kind of want to switch gears and get away from just the research that I'm doing, but one of the motivating factors for the research and for the work in general that I do at University of San Diego is involving undergraduate students in research. And I think this is a motivation shared by a lot of the other Cottrell scholars and by Research Corporation in general. And I've kind of learned a lot and been supported in many ways in my desire to involve undergraduate students in research, not just through kind of financial support through the Cottrell Scholars Award, but also just learning from others about kind of best practices in conducting undergraduate research or working with undergraduates in research, developing course materials that help undergraduates get involved in research. They have a great publication here on kind of course-based undergraduate research experience, which I've used to help me develop some of my courses. And I also want to talk about how the research that I do, how I think it's the best kind of research for involving undergraduate students. Maybe not really the best, but it's great for involving undergraduate students. And that's for a couple reasons. One, the kind of work that we do is great at directly observing fairly complex or abstract concepts. And I'll just quote a view I share here. This is from Sidney Nagel. That soft matter is great because students can see and sometimes even feel the phenomena, and they can come up to speed relatively rapidly then, right? And I'll just highlight that with one of the projects we've been working on. So again, the same kind of system where we have a fluid-fluid phase separation with a colloid polymer system. I'm now showing with the fluorescence images, so we see these droplets emerge, right? The colloidal particles have just been fluorescently labeled. We're able to identify these droplets, track their growth, measure the growth rate of these droplets, as well as just observe the fluctuations at the surface of the droplets. Right, so students who are doing this are learning about kind of surface tension, capillary waves, critical nucleus size, these kind of complex and abstract concepts that you're maybe teaching in stat mech, but here they're seeing it visually. They're getting tangible results. All right, the other reason I think looking at soft matter physics is exciting and is great for involving undergraduate students is that it highlights concepts that unite fields. And again, I'll quote somebody whose view I share, Sam Saffron. Right, the soft matter may be the best way to expose students in science and engineering to themes that unite various scientific fields by their relation to statistical thermodynamics and dynamics of interacting many particle systems. Right, so I had a student, Caroline Riestra, graduated last year. She's now getting her master's degree. She was working on a project looking at liquid-liquid phase separation, similar to using a system similar to the colloid polymer system I described before. And she was measuring, the viscosity and the surface tension of these droplets, looking at how these droplets coalesce. But the themes covered in this work that she was doing are seen in other fields too, particularly in biology, where in the kind of trendy field of biomolecular condensates and membranous organelles, these ideas of coalescence and surface tension and viscosity come up a lot. And so with Caroline, we're able to publish the kind of work that went into developing this undergraduate research lab into this paper, which just came out in the Biophysicist. And I want to bring this up because, one of the program directors at Research Corporation is an editor on this, Andrew. And also in the first issue of the Biophysicist, there's a number of Cottrell scholars. I think it's majority Cottrell scholars. Wait, so I think that speaks to, maybe that speaks to cronyism, hopefully not, right? I think that speaks to the kind of interest that the Research Corporation has in interdisciplinary work, right? Work that unites themes from different fields and in educating students in this interdisciplinary field. All right, so with that, I just want to and thank, again, my lab members here, and thank Research Corporation for their funding, which has led to other funding, and it's been a great source of support. So thank you.